Hey, it's me, Mr. Truman, back again for another lesson in geometry. Today we're going to be going over symmetry, and we're going to be talking about three types of symmetry, one called reflectional or line symmetry, rotational, and point symmetry. So I'm going to be explaining each one of these as we go along, but I'm going to start with the first one called reflectional symmetry. And reflectional symmetry is also sometimes called line symmetry, because basically what we're asking is, can you draw a line down the middle of that figure and make it so that that figure would fold onto itself? We like to think of ourselves as having a line of symmetry running right down the middle of our face. Well, that's what we're looking for here. We want to look at each figure and determine whether or not we have this type of symmetry, reflectional, or if you will, line, either one. And then we're also going to check on something called rotational, meaning can I take this figure and turn it so that it lands on itself if I was to rotate it a certain amount of degrees. And then the last one's called point symmetry, which I'm going to explain in a moment. I'm going to hold off on that for the time being. So when I look at this equilateral triangle, one of the first things I'm going to look at to determine whether or not we have symmetry is I'm trying to look at the shape to find out if it's what you call regular. In geometry, when we say a figure is regular, that means that all the angles have the same measurement and all the sides have the same length. So when I look at an equilateral triangle, that is a triangle that has all three angles the same and all three sides the same. With that being said, because it has three sides and it's regular, it now will have three lines of symmetry. It'll have one going right up the middle like this, and it'll have one going right across, and it'll have one like this. So it has three lines of symmetry because any of those lines, had I used an actual ruler and made it look nice, would show you that you could fold that triangle onto itself. So it has what you call line symmetry. So it has three lines of reflection. I'm just going to abbreviate reflect. All right. Now, when it comes to rotational, I want to know if I were to take and put like my finger right in the middle of that shape, could I rotate that around clockwise or counterclockwise? Either way, it doesn't matter. But can I rotate it around if I put my finger right dead in the middle, and can I rotate around and have it so that this one will land on top of this one, and so forth. So in this case, because it's an equilateral and we know that every angle is the same, that means that each of these points is kind of at the same angle, or is at the same angle. Therefore, I can rotate this, and if I take this and bring it around, it'll land right here, and it'll be right on top of itself. And so that's called rotational symmetry. Now, when we talk about rotational, though, we have to be very specific. We have to give the angle of rotation. And the way we calculate that is we take the number of degrees in a shape, which is 360 for a rotational around, and we divide that by the number of sides, which in this case is 3, giving me 120 degrees. But that's not my only angle of rotation, because I still could go, if I turned it once, this at 120 degrees will end up here. But I could do that one more time and get it to here, which would be 240 degrees. Now I don't list 360 because if I list 360, that means I've gone all the way around and I'm back to where I started. So when I talk about rotational, I want to list each one of the movements I could rotate it so that it lands on itself. Now, point symmetry is when you do a rotation, or you find that you have rotational, and one of the numbers that you can rotate to is 180, we call that point symmetry. And we'll see that in a few minutes. All right, so not every shape is going to have what we call lines of symmetry. For example, this is an isosceles right triangle, meaning two sides have the same length. This one and this one are going to have the exact same length. And they're even going to have these angles be the same, because that's how an isosceles triangle works. If you have two sides the same, you have two angles. But when it comes to lines of symmetry, something doesn't work here, because if I put this right in the middle, I don't have the ability to fold it onto itself. If I draw a line vertically, it doesn't work. Same thing goes with horizontally. That one doesn't work either. I fold it this way, it doesn't work. But what if I took and I picked it up like this and I drew it? can I reflect it, or can I draw a line this way? And the answer is yes, I can. This side can fold onto that side. Now the reason that happened is because I had two angles and two sides that are the same length. So they created something that I could mirror image over on itself and create a line of symmetry. So because it had two matching angles, I produced, in this case, a line of symmetry. So I have one line of symmetry of reflectional. All right, and as for rotating it though, let's check that out. So when I go to rotate it, if I were to turn this, I don't think there's anywhere, if I put this in the middle, my finger right in the middle of this, there's no way I'm going to be able to rotate this and have it land on top of itself. Because it's always going to be moving around, and this one's going to come around, and they're just never going to be, it's never going to be on top of itself. So there's no lines, or there's no rotational. All right, which means there's also no point. So when I look at a figure like this last one, or this last triangle I want to go over, this is called a scalene triangle, in which none of the sides are the same and none of the angles are the same. How many lines of symmetry do you think you'd have if none of the lines, none of these sides are of the same length? And the answer is going to be 0. Because if I try to draw a line vertically, it doesn't work. If I try to draw a line horizontally, it doesn't work. And if I tried to draw a line diagonally, it doesn't work. There's nothing I'm going to be able to do. And that's because of the fact that none of the sides have the same length. Therefore, it's never going to have any lines of symmetry. So in this case, there's no lines of symmetry, or no lines of reflection. There's no rotate, because I can't rotate it. There's nowhere I can put my finger in the middle of it and spin it around. It's never going to land on itself. And that's, again, goes back to the fact that this is not a regular shape, just like this was not a regular shape. Therefore, it's not as easy to figure it out. This one having nothing in common, there's no lines of symmetry. So let's get back to some shapes that we do know have lines of symmetry, and that would be something that is regular, like this pentagon. 5-sided figure, all angles are the same, all sides are the same. This has 5 lines of symmetry. I can draw a line this way, this way, this way, and so forth. It has 5 lines of reflection. It also has rotational, because if I put my finger right in the middle of this, I can spin this around, and every time I can get this one to land here and so forth all the way around, because of the fact that the angles are all the same. So let's calculate each of those angles of rotation. So I'm going to start with 360, divide it by 5, and I get the number 72. So if I put my pencil right there and I move it to the first position, that's 72. 72 plus 72 tells me my next one is 144. Add that again, I'm going to get 216. And then that last time, let's see, there's 72, 144, 216, and the last one will be 288. And each of these are your angle of rotation, so it can be rotated 4 times, and then on the 5th one, it lands back where it started. So we don't list that one. All right, on a dodecagon, I'm not going to draw the lines, but I'm going to tell you right now that a dodecagon, do stands for 2, and decagon stands for, deca stands for 10. This is a 12-sided figure. So automatically, we should be able to figure out, because it's regular, there are 12 lines of reflection. Now, when it comes to the angle, this is a big one, because if I take this one, it's 360, and I divide that by 12, I get 30 degrees, which means my very first time I make that rotation, it's 30, 60, 90, this is going to take a while, 120, 150, 180, going to need another line over here, 210, 240, 270, wow, oh my gosh, I hope we don't have to list any problems like this on our homework. It's got a lot of rotational because it has so many sides. Now, because one of those numbers, this is 12 lines of reflection, all these angles of rotation, and then because one of its rotations is 180, we say this has what you call point symmetry. On top of having line and rotational, it has point symmetry. All right, I'm going to take two last figures here that are a little bit out of the geometric world and just kind of use a couple car symbols, because anybody who knows me knows that I'm always into cars and motorcycles. So if I look at the old symbol for Chevrolet, I notice about this that it has no lines of symmetry because there's nothing regular about this shape, and it has no lines of symmetry. Vertically, horizontally, diagonally, it's never going to work. But it does have rotational. I could take this, flip it upside down, and what do you know? It's the same exact thing. It has rotational. Now, I'd have to rotate it exactly 180 degrees. So, no lines, rotational, 180. And by the way, if you rotate 180, that means you also have what's called point symmetry. So we want to make sure that if they ask us about a question like this where we only rotate, or we rotate 180, we have point. And then the last one is the old VW symbol. I like this one here. This one has no rotational symmetry, but it does have line symmetry right down the middle. One line of symmetry. Or, yeah, one line of reflectional. All right, well, I hope that clears it up. I hope that sums up what it means to have symmetry, and that's it for me. Bye.